Here's a graph. Starting from A. Visit every node you can reach. Simple enough. But the order you visit them in matters a lot. And there are two fundamentally different ways to do it. Breadth first search. And depth first search. Same graph. Same starting point. Completely different visiting order. Notice this graph has a cycle. A to B, B to E, E to F, F to C, and C back to A. If you explore neighbors without remembering where you've already been, you can walk in circles forever, revisiting the same nodes endlessly and never actually finishing. The fix is simple but essential. Keep a visited set. The moment you arrive at a node, mark it. Never explore from an already visited node again. That one habit is what turns wandering around a graph into an algorithm that's guaranteed to finish. Once you're tracking visited nodes, there's still a choice. Which unvisited neighbor do you explore next? That choice is the entire difference between BFS and DFS. Breadth first search uses a queue. You explore nodes in the exact order you discovered them. First in, first out. That naturally explores everything one ring outward at a time. Level by level. Depth first search uses a stack instead. Or just recursion, which behaves the same way. The most recently discovered node gets explored next. That means you commit to one path and follow it as deep as it goes before backtracking. Visit A, order 1. Add B, C to the queue. Visit B, order 2. Add D, E to the queue. Visit C, order 3. Add F to the queue. Visit D, order 4. No new neighbors to add. Visit E, order 5. No new neighbors to add. Visit F, order 6. No new neighbors to add. BFS visiting order. A, B, C, D, E, F. Notice it fans out in rings. A first, then both its direct neighbors, then the next layer out. This is exactly why BFS is the go-to for shortest path on an unweighted graph. It reaches closer nodes before farther ones. Guaranteed. Visit A, order 1. Go as deep as possible first. Visit B, order 2. Go as deep as possible first. Visit D, order 3. Go as deep as possible first. Dead end at D, backtrack. Visit E, order 4. Go as deep as possible first. Visit F, order 5. Go as deep as possible first. Visit C, order 6. Go as deep as possible first. Dead end at C, backtrack. Dead end at F, backtrack. Dead end at E, backtrack. Dead end at B, backtrack. Dead end at A, backtrack. DFS visiting order. A, B, D, E, F, C. Completely different from BFS. On the exact same graph, DFS commits to a path. A, B, D, hits a dead end, backtracks, and only reaches C dead last. Because it finishes exploring everything down the B branch first, this depth first commitment is exactly what makes DFS the natural choice for problems like finding a path, detecting cycles, or exploring every possibility with backtracking. Reach for BFS when you need the shortest path on an unweighted graph, or anything framed as closest first. Level order traversal of a tree is a classic example. Reach for DFS when you're asking, does a path exist, finding connected components, or solving anything that needs backtracking, like generating permutations or detecting a cycle. Both visit every node and edge exactly once. So both cost O of V plus E. The difference is purely about order, not speed. BFS and DFS solve the same underlying problem. Visit everything reachable exactly once, using the same core rule. Track what you visited. The only difference is queue versus stack. And that single choice completely changes the order and which real-world problems each one is suited for. Next up, Dijkstra's algorithm. What happens to this exact idea once edges have different costs? Not just a single step each. If you want every pattern explained with the reasoning, not just the answer, subscribing means you won't miss the next one.